What happens when you throw a ball into the air? It doesn't just go straight up and down, it follows a curved path. That curve is what we call a trajectory, and the motion itself is called projectile motion. A projectile is any object that's launched into the air and then moves under the influence of gravity alone. No engines, no wings, no propellers, just gravity pulling it down. Think of a basketball shot, a soccer kick, or water spraying from a fountain. All of these are examples of projectile motion. In physics, we often simplify things to make them easier to analyze. So when we study projectile motion, we usually assume a few things. First, we ignore air resistance. Second, we treat gravity as constant, about 9.8 meters per second squared, always pulling straight down. Third, we assume the Earth is flat over the distance the object travels. And finally, we treat the object as a point mass, meaning we don't worry about its shape or spin. Under these assumptions, the path of a projectile is always a parabola. Here's the key idea. Horizontal and vertical motions are independent. That means what happens in the horizontal direction doesn't affect what happens vertically, and vice versa. Imagine you drop one ball straight down and launch another ball horizontally from the same height at the same time. Which hits the ground first? They both do, because gravity pulls them down at the same rate. The horizontal motion doesn't change how fast they fall. So, in projectile motion, horizontal motion happens at constant speed. There's no horizontal acceleration in the ideal model. Meanwhile, vertical motion is affected by gravity, so it accelerates downward. These two motions happen at the same time, but they don't interfere with each other. Now, let's say you launch something at an angle. Maybe you kick a soccer ball at 35 degrees above the ground with a speed of 20 meters per second. To analyze this, we break the velocity into two components, horizontal and vertical. The horizontal component is v naught times cosine theta. The vertical component is v naught times sine theta. So in this case, v naught is 20 and theta is 35 degrees. You'd calculate v naught x as 20 times cos 35 and v naught y as 20 times sine 35. The horizontal component tells you how far the ball will go. The vertical component tells you how high it will rise and how long it will stay in the air. Once you have those components, you can use the equations of motion. For horizontal motion, since there's no acceleration, the position is just x equals v naught x times t. The velocity stays constant. For vertical motion, the position is y equals v naught y times t minus 1/2 gt squared. The vertical velocity is vy equals v naught y minus gt. If you eliminate time from these equations, you get a formula for y in terms of x, and that gives you the parabolic shape of the trajectory. From these equations, we can predict a lot. For example, the time to reach the highest point is when the vertical velocity becomes 0. That happens at t equals v naught y divided by g. The maximum height is v naught y squared divided by 2g. The total time of flight, if the projectile lands at the same height it was launched, is 2 v naught y divided by g. And the range, or horizontal distance, is v naught squared times sine of 2 theta divided by g. That last one is interesting. It tells us the maximum range happens when the launch angle is 45 degrees. But that's only true in the ideal model. In real life, air resistance changes things. Speaking of real life, where do we see projectile motion? Everywhere. In sports, it's in basketball shots, soccer kicks, baseball throws, golf drives, and javelin throws. In everyday life, it's tossing your keys, throwing trash into a bin, or water coming out of a hose. In engineering, it's in fireworks, bullets, and even accident reconstruction. In nature, it's in seeds ejected from plants or droplets from a sneeze. But remember, the real world isn't perfect. Air resistance slows things down. It makes the path steeper on the way down than on the way up. Wind can push a projectile sideways. Spin can cause it to curve. This is called the Magnus effect. That's why curveballs in baseball or bending free kicks in soccer don't follow perfect parabolas. And over long distances, gravity isn't constant and the Earth's surface curves. That's when we move into orbital mechanics. Still, the basic model is powerful. It helps us understand and predict motion in a wide range of situations. So, to sum up, projectile motion is the motion of an object launched into the air, moving under gravity alone. Horizontal and vertical motions are independent. The path is a parabola in the ideal case. We can calculate time, height, and range using simple equations, and we see it all around us, in sports, in nature, in technology. Understanding projectile motion gives you a deeper insight into how the world moves.